Hello. I am Audit Khan, Assistant Professor of Basic Science Department at Gargi Memorial Institute of Technology. So, today's our lecture on statistical mechanics. Okay, students. So, first of all, we have to know about the three things. One is called. So, today we are studying statistical mechanics. Okay, statistical mechanics. So first of all, we have to know about what is statistical mechanics. We need to three things. It's called microstate, macrostate, and phase space. So what is this? First of all, so for the study of the microstate and the macrostate we to define these two terms we need an example. Okay, let we have two particles to be distributed in two identical box. Okay, so we have a two particle or two balls. Those balls are made by same plastics or same material. We distributed these two particle or the two balls in a two identical box. The two box are also a similar box. The dimension of the box and the characteristics, any physical characteristics of the box are similar. So we try to distribute these two ball or the two particle in a two box. If let the box, the ball or the particle is indistinguishable. Indistinguishable means you cannot just think that your eye is closed. I give you a two ball. We cannot separate these two ball by through these characteristics or color or anything else. You have to think that the two balls are equal and every characteristics of these two balls are equal. So such type of particle or such type of things is known as indistinguishable. You cannot find any type of difference between this two in any kind of differences in these two things or two particle or two box. So that's why the two particle or three particle, everything is similar to you. That's why such type of particle is known as indistinguishable. You cannot find any type of differences between such type of particles. Okay, so if you distribute these two particle in a two box, you have, suppose this is a two boxes. You have to distribute in a two balls in this box, no ball in this box. Maybe if you distributed, this one is 1 1, or if you are maybe distributed is in 0 2. Clear? The probability of the two balls in this box and no ball in this box is 1/3 probability. Probability is 1/3. They have also probability of 1/3. They have also probability of 1/3. So we have a total 3 arrangement of the distribution of the two particle in a two box. So that means number of arrangement is equal to 3. We can rewrite is 3 is as like 2 plus 1. We we see why I am writing here 2 plus 1. Okay, next case 2. Suppose this is the case 1 for the indistinguishable case 1. Okay, in the case of the case 2, let the particle is distinguishable. That means now you can open your eyes. You can see that you have a one red ball, one green ball. So now you can distinguish these two particle or two balls, that you have a two specific color of this two specific ball. Now you have to distribute these two ball in a two boxes. You have arrangement of, you have a obviously a two box. Suppose you have a red ball, red and green. Okay, you put here red and green. Here is no ball. You put here red, here green, as well as if you can put here green, here red, or if you can put here 0, here red and green. Now the probability of, so in the case of the distinguishable arrangement, we have a 4 arrangement of state. We can distribute it, this distinguishable particle or a ball, in a 4 type of state. But in the case of the indistinguishable case, we have a only 3 state. But in the case of the distinguishable, we have a 4 state, because we know we can distinguish these two ball or the particle by through its color. Okay, so that's why such type of things is known as distinguishable. So the probability 1/4, probability 1/4 plus 1/4 is equal to half. The distribution of such type of things, the probability is 1/4. Clear? So the number of arrangement, the number of arrangement is equal to 4, because we have a 4 arrangement. We can rewrite here 2 square. Let's see why I written here as 2 square. Okay. Now we take another example. In this case, we distributed the 3 ball in 2 box. Case 1, indistinguishable. So we can distribute it here like 3 0, 2 1, 1 2, 0 3. The probability 1/4, 1/4, 1/4, 1/4. Is it clear? This is the probability. They all have a equal probability. We can rewrite equal probability. Okay, those all state have a equal probability. Clear? So now the total number of arrangement is obviously 4 arrangement we have here. We rewrite here 3 plus 1. Clear? Let's case 2, distinguishable. So we have a 3 ball. So we chosen the color of red, green and blue. Clear? Now you distributed these 2 ball in a 3 ball in a 2 box. Red, green, blue, 0. green, blue, red, green, blue, red, blue, green, red, as well as we can distribute like that: red, green, blue, green, blue, red, blue, green, red, as well as the fourth one is 0, red, green, blue. So what is the probability of this one? 1 by 8. This one is 1 by 8. This one is 1 by 8. This one is 1 by 8. The total is 3 by 8, as well as 1 by 8, 1 by 8, 1 by 8. This is the probability. The total is 3 by 8, and this is 1 by 8. The probability. Clear? So the number of arrangement equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. We can rewrite like 2 cube. So what is signified by that? This one and this one. In the first case, we distributed the 2 ball in a 2 blocks. That means 3 ball in a 2 box. This is signify that number of particle plus 1. That means the total arrangement of the 3 ball in a 2 box is signified by the total number of particle plus 1. And in that case, in the indistinguishable case, or in the distinguishable case, it is rewrite as a number of box whole to the power number of particle. Clear? Number of box is 2 and number of particle 3. So now we are going to a identical case. Let's choose n number of particle is distributed in 2 box. What is the case? First case, indistinguishable. Now put n 0. N number of particle is here. There is no particle. Now this box has n minus 1 number of particle. This box has n 1 particle. Now this box has n minus 2 particle. This box has 2 particle. Go on. As an arbitrary case, you have n minus of r particle is here. Obviously, the r particle in here, and go on. Last case is obviously the 0 by n particle. And we can see that in that case, in the indistinguishable case, every state the probability is equal, and probability is signified by (1 by n plus 1) actually, because this is 1 by 4. So it is defined by 1 by 4. That means 1 by number of arrangement. Clear? As well as same thing is here for the distinguishable case. The probability is equal to 1 by 2 to the power n. Clear? So in the case of the n particle, every probability is equally probable. Everyone has probability 1 by n plus 1, 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 because they have a n number of particles. The arrangement, the total number of arrangement must be n plus 1. So obviously the probabilities become equal to 1 by n plus 1. Is it clear? So this is the indistinguishable case. In the case of the distinguishable, case, so we have a n number of particles. Suppose the n number of ball, n number of ball have a n number of different colors. So you have to distribute in a various way. So we chosen this case for the distinguishable case. The probability of this arrangement is coming from the probability is written by n factorial divided by n factorial minus n minus r whole factorial. This is the distribution function. How can you distribute the n number of particles in a way of r particle is here and the rest of the particle is here, is coming from the permutation distribution formula. You just see the mathematical chapter of the 11 or 12, the permutation and distribution function. The permutation distribution function of the total n number of particles is distributed in that way. The r particle in here and the rest of the particle in here is mathematically represented by this equation. Is it clear? So this is the distribution. Total distribution. How many number of arrangement we have for this function is this one. We can get from this mathematical term. How many arrangement you can put the value of the r in here, just you get the distribution. How many number of distribution you have for this function, you get by this mathematical form. Is it clear or not? Okay, so and again the total number of arrangement is written by 2 to the power n, because we have a 2 box and n number of particle. I have already write here the arrangement is for the distinguishable case. The arrangement can be written as a number of box to the power number of particles. So number of box is 2 and the number of particle is n. So the probability is obviously 1 by 2 to the power n. Clear? Suppose this is the we can see that in the two cases of the both distribution case, this is the most probable state, because such type of probable state have a greater number, because we have the probable state like that there is a 0, there is a all particle is here, the probability is 1 by 8. But in the case of the 1 particle is here and the 2 particle is here, they have a 3 by 8, the number is greater than this one. So we can say that this 2 state is the most probable state. From this arrangement we can think that this state is the most probable state. So the probability of most probable state is n factorial by n factorial divided n minus r whole factorial into 1 by 2 to the power n. this is the probability of the most probable state. The number of distribution into total probability. This is the probability of the most probable state. So what is the difference? This one is called macro state of the particles, and this one is called micro state of the particle. Is it clear? So for the distinguishable case, you cannot be distinguish or separated the particle by through its characteristics. Such type of distribution is known as macro state distribution. And in the case of the you can distinguish the all particle by through its characteristics. Such type of state is known as micro state distribution. Clear? So you can rewrite the definition like that. Micro state is the arrangement of the particle of a system without distinguishable. Clear? Similarly, it is a macro state. Micro state is the arrangement of the particles of a system with distinguishable. Is it clear? Now if you can clear the idea of the micro state, which one is the micro state and which one is the macro state, in the case which particle cannot be distinguished, that means those particles are indistinguishable. You cannot separate those particles by through its characteristics. Such type of distribution, you just distribute the particle in some boxes. The distribution is one type of kinetic theory of matter. In a one box you have a 1 mole of gases, that means 6 into 22 into 10 to the power minus 23 number of particles. Now you separated this 1 mole of gas in a 2 box. You just separated this 1 mole gas in a 2 box. That means the total number of particles is divided by the 2 boxes. So 6.023 into 10 to the power 23 by 2 for the each box is the most probable state. So we can see here. That's why this one is called most probable state, because in a equilibrium we can see that the total number of particles is divided in the 2 boxes by a similar way. Clear? Okay. If there are n particles to be distributed in 2 boxes, then number of macro state, obviously n plus 1, number of micro state is equal to 2 to the power n, number of box whole to the power number of particle, and macro state is defined by the number of particle plus 1. Okay, So number of micro state when r particle in r particle in two boxes is n factorial r factorial n minus r whole factorial. Is it clear? So number of, okay, this is the total number of r particle. If you distribute the r particle in a total n number of particle, with one box have a r number of particle and the rest of the particle in another box, the total distribution of such type of permutation combination is coming from this equation. Is it clear? So one thing is that you can always see that the you can rewrite that number of microstate in macrostate may be equal to macrostate or greater than macrostate. So we can see that the microstate, the macrostate, this one is a macrostate and this one is a microstate. So always the macrostate must lesser than the microstate. So we have here the significance. This is the significance. The significance of two cases is the microstate must be equal to the macrostate or greater than to the macrostate, but never be microstate is the less than the macrostate. Is it clear? Okay. So let's see some example. Suppose you have, okay, let's see some example. Okay, you have a 10 particle is distributed in two boxes. So what is the microstate probability? Probability is 1 by 2 to the power n, that means 1 by 2 to the power 10. It is coming from 1024, and macrostate probability is 1 by n plus 1. It is coming from 1 by 11. 10 plus 1 is equal to 1 by 11. So you can see that the microstate is always greater than the macrostate. Sorry, microstate always less probable. It is a less probable. The probability is always less in the microstate because the distribution of the microstate always greater than the macrostate. I am here written here the number of microstate always be equal or greater than, that means the obviously the probability is become lesser in a microstate than the macrostate. So you can say me that why we read such type of things, the statistics of in a statistical mechanics, the microstate and macrostate. Now you can assume that the What is the application of such type of macro state and the micro state? Suppose you have a 2 box. You have 1 mole of oxygen. So there is a oxygen, there is a vacuum. So 1 mole of oxygen means 6.022 into 10 to the power 23. Clear? The probability of this case, probability is this case 1 by 2 to the power 6.022 into 10 to the power 23. So this is a much less probable. We can see that. Clear? Less probable in a micro state. So obviously, if there is some door in between these 2 boxes, the oxygen is whole oxygen is situated in this box. There is a vacuum. If suppose this layer have some little open space, so obviously oxygen is flowing from this side to this side. In a certain case, the total number of oxygen molecules. The total number of oxygen molecule is separated by these 2 boxes. That means 6.022 into 10 to the power 23 divided by 2 and 6.022 into 10 to the power 23 divided by 2. This is the total number of particles in the most probable case. Most probable case. This is the actual application. Because in a statistical mechanics, we have a gas chamber, and this gas chamber have a certain number of molecules. So you have to need the most probable state. That means the number of molecules is distributed by the such number of. You have a, suppose there is a not only a 1 box. You have a multiple number of box. Every box have a certain number of gases, certain value of gases. So certain value of gases have a certain number of particles. If every box is separated by some such type of wall, then the gas can flow from one box to another box. So in that case, the whole gases and the whole box is distributed by in a equilibrium. So that equilibrium case is known as the most probable case. It is very important for the further study of the quantum mechanics. Is it clear? So this is the most probable state. Okay. So today we are studying about the microstate and the macro state. Next day we just see some basic term of the statistical mechanics and the condition for the most probable state and the condition for the minimum probability of the state. This is the most we can see that this is the most probable state, but we cannot derive the such type of equation in this lecture. So in the next lecture we just we just try to develop the equation for the most and the maximum and the minimum probability state of a boxes. Okay, thank you.